All right, so moving along here, the example, determine the magnitude of the force. So again, doing a bit of decoding here, magnitude of force. So we are looking for force, it's our unknown, between two spheres 1 meter apart, so we know the radius, and equal charges. So Q1 equals Q2, which is the 1 times 10 to the negative 12 coulombs. So we're just applying Coulomb's law. Fe equals Q1, Q2, don't forget my K, R squared, R1 squared. So plugging in the values, 9 times 10 to the 9th, and then 1 times 10 to the negative 12. Now they're the same, so I'm going to be efficient, not lazy. I'm going to square them. And then we have 1 meter squared in the denominator. And when you punch that in, 9 times 10 to the negative 15 newtons. Okay, so fairly inconsequential, but that would be the force of repulsion in this case between two charged particles with those conditions. And that's it. So moving to something a little bit more challenging, we have spheres A, B, and C. It says that A and B are fixed in position and have those charges, 4 times 10 to the negative 6, negative 2.5 times 10 to the negative 7. We want to know what is the net force acting on C, who is a charge of 6.4. So there is a force of attraction between B and C. Okay, so I'm going to call this force BC because they are attracting each other, they're pulling together, and there will be a force of repulsion. And that's because of the forces acting on A and C. So that means our net forces then, so F unbalanced, Fu, will equal force AC minus force BC. Okay, so there we go. We're just finding the resultant force on those two forces that are acting. Now, when we do the substitution here, I want to do this without putting the numbers in first. So I'm going to change the subscripts on the Q's to A's, B's, and C's. So if we go K, Q, I'm doing AC first. So QA, QC over R1 squared minus K, and then QB, QC over R2 squared. If you want, you can factor the K's out. It's not a really big saving, or not a ton more efficient anyway. Or you can factor out the QC's as well. So you can go K, QC since it's common to both. And then you just have QA over R1 squared minus QB over R2 squared. Does it save you a lot of time? Not really. It makes the calculations a little bit easier, but it's not going to be the end of the world if you don't do it this way anyway. So doing our substitution, K is 9 times 10 to the 9th. QC, it is the common factor here, 6.4 times 10 to the negative 6. Excuse me. QA is 4 times 10 to the negative 6 divided by, and its distance at this point in time, got to be in meters, so 0.3 squared, minus the charge of the other one is negative 2.5 times 10 to the negative 7th divided by, and its distance is 0.1 squared. So you'll notice that you are subtracting a negative here. All right, so just be careful of that when you're using your calculator. When you go through and punch that all out, you get a net result of 1.12 newtons. And it will be to the right because it is a positive solution. So if I follow along with the XY axes, right? So I'm assuming that to the right and up is positive because it comes out to be positive 1.12. Then the resulting direction would be to the right. Okay, so charge C is actually being repulsed. So therefore, C is being repulsed by 1.12 newtons. Right, and there you go. All right, so you're just looking at the difference. Now we're just looking at unbalanced forces, and we're just using different equations to calculate them. All right, same concept as what it was in grade 11. So identical spheres, A, B, C, and D, with the charge magnitude of that, so they all have the same charge, are situated on the corners of a square. So, giving myself a diagram, A, B, C, and D, they are on the corners of a square. They all have the same charge, so Q1 equals Q2 equals Q3 equals Q4, which is the 5 times 10 to the negative 6 coulombs. Sides are 25 centimeters in length. So I'm going to convert that to 0.25 meters. Two diagonally opposite charges are positive. Whoops. So they're not all the same charge. The opposites are positive and negative. So let's go with, it doesn't really matter if you're to do this question. I'm going to say that these two guys are positive, making B and C negative charges. And down below here, to make this statement true, because I don't want to erase it, put the magnitude symbols in. So the magnitudes are all the same. All right. So what do we want to do? We want to calculate the net force acting on each of the four spheres. Okay, well, we can just do a free body diagram here. And because everyone has the same charge, then we have a symmetrical situation. So because everything is symmetrical, we only have to really analyze one of the charges. So let's look at, it doesn't matter which one we pick, free body diagram for A. All right, so there is the free body diagram for A. So what is happening here? Well, we know that there's a force of attraction between A and B. We know that there's a force of attraction between A and C. And finally, D and A, there's a repulsive force right here between A and B. And it's at an angle. Now that angle, because we're dealing with a square, that angle will be 45 degrees. So I know that all of you have been upset we haven't been doing vectors lately, so now we slide back into our vector mode. All right, and vector mode tells us that if I take FAB plus FAC plus FAD, I will find my unbalanced force. So we're just going to convert each one of these into vectors. So, excuse me, for force AD. So we need to know the force that's involved there. Well, it's at a 45, so it's going to be equal to K, so 9 times 10 to the 9th, Q1 and Q2. So that would be A and D are the same charge. So it's 5 times 10 to the negative 6 squared divided by, now I got to find the distance from A to B. All right. So over here, distance of AD. So I know it's a right angle triangle that gets formed here. So C squared equals A squared plus B squared. So we end up with C is equal to the square root of 25 squared plus 25 squared, which is 35 centimeters or 0.35 meters. So I need that in order to continue my calculation. So that would be over 0.35 squared. Now that is going to be negative, again, remember our vectors, negative x component, positive y. So I got to put that negative in. So that's I plus, oops, I need my 45 as well. Skipping stuff here. Oops, I don't want to do that. Let's move it over, give me a little bit more room. That would be cos 45 I plus 9 times 10 to the 9th, 5 times 10 to the negative 6 squared over 0.35 squared. I still don't have enough room here. So just extend that down for a sec. I'm going to move it down here. So then I have sine 45J. So there is my FAD. FAB is to the right, so it's going to have no J component. That's just to the right. It's in the positive direction. So FAC, whoops, am I doing the right one? FAC is down, my mistake. So I was off by one. It has no X component, minus, because it's facing downward FAC, 9 times 10 to the 9th. And then we have 5 times 10 to the negative 6. And they are opposite charges. So negative 5 times 10 to the negative 6 over 0.25 squared. And then FAD is the one I was thinking of. It has no Y component. Excuse me. So 9 times 10 to the 9th. 5 times 10 to the negative 6. Negative 5 times 10 to the negative 6. That would be an I over 0.25 squared. So this becomes an exercise in who can use their calculator the best. So setup is so important here. You understand why I'm looking at or analyzing the process. Excuse me. So you go ahead, and if you got to do it in steps, you got to do it in steps. But be very careful with the calculator. And as I calculate this, I get 2.3I minus 2.3J. So the unbalanced force is, both of them turn out to be 2.3. And you can see there is symmetry when you look at the two columns when you're doing the adding and subtracting. So the magnitude of the force unbalanced, going back to our vectors, we find that the unbalanced force is 3.25 newtons. I know theta is 45. I don't have to do the calculation here because A and B, the opposite and adjacent, are the same. So therefore, unbalanced force, Fu, is equal to 3.25 newtons. Following or looking at this, the X component here was positive. So that means that it's going to be the right or east, doesn't matter which one, 45 degrees. This component is negative, so it's going to be down or south, whichever way you want. So it turns out that it's 3.25 newtons right, 45 degrees down. So we're actually, the force acting on it, or the net force, I should say, is that it's heading in this direction. So there's my unbalanced force for you. Okay, that's what that tells us. So there we are. So that, of course, it's one of the more challenging questions, obviously, because of the math involved. You have to remember my emphasis and focus is on process. Process is very important. So if you make a calculation mistake, but you set this up properly, you're not looking at devastating mark reduction because it's that process that's so important. So you do want to take some time and care when you're doing the calculations, but remember, it's not the be-all, end-all. Don't get frustrated when you make small mistakes. They iron themselves out in the end. So I think I put the homework over here. Whoops. So this is the assigned homework for us. Okay, out of the textbook. If you have any questions, you obviously know where I'm going to be tomorrow, and we'll get you moving along.